So, we've had our discussion of what happens to the sun in the future, and that was pretty interesting. And we talked about all kinds of options about what can happen to the remnants. I said that I would come back and say what happens with more massive stars, and the time to do that is now. So, we start with a star whose mass is bigger than 8 solar masses. That turns out to be a good place to make the cutoff. Between solar mass and 8 solar masses, there are some changes, but these two extremes will give us a representation of what happens. Star with massive star can finish its main sequence life in as little as 10 million years. So these stars are ephemeral compared to the sun, 1,000 times faster. And as usual, main sequence was when it was fusing hydrogen in the core. When the core runs out of hydrogen, the core contracts, the envelope expands and cools, and we get a red giant, except because it started out as a big star, we might get something we would call a red supergiant. So this happens within 1 million years of the core collapse. It's finished its red giant expansion stage. Its size can be 5 astronomical units. We have a hydrogen burning shell surrounding an inert helium core and a huge extended envelope. There will be mass loss in this period. The only difference is that here the inert helium core is too big. It never actually becomes inert. It's a smaller fraction of the actual mass of the full star, so it does not collapse because of degeneracy, but the core becomes massive. Eventually, it's not its own gravity, but it is compressed by the external layers. The internal temperatures were already high enough, and so this is the red supergiant phase. Notice that there's not a huge increase in luminosity at this point. The outer layers are cooling rapidly as the star expands, so that luminosity rises somewhat, but not very much. This was already a 100,000 solar luminosity object. It doesn't get that much more luminous as a red giant. And as usual, helium core ignites. It's not as flashy, but since we don't see the flash, that makes no difference. We now have the structure where we have helium fusion in the core, hydrogen fusion in a shell, the envelope, the hydrogen fusing shell having expanded, reduces its rate, the envelope contracts and heats. We have the horizontal branch for this giant star. It makes a blue supergiant. It's moving over to the left of the diagram. It's becoming blue. It lives on the horizontal branch, remember, not 700 million years, but only 1 million years. And again, the helium fusion in the core is rapidly depositing a carbon-oxygen core surrounded by a shell of inert fusing helium, surrounded by inert helium, surrounded by hydrogen that is fusing, surrounded by the inert hydrogen atmosphere. And here is where things become interesting. When the carbon-oxygen core collapses here, it does reach a temperature, 600 million K, at which carbon nuclei can fuse. And the carbon fusion process produces things like manganese and neon, magnesium and neon and oxygen. And so we now have a collection of an inert oxygen neon core surrounded by a carbon burning shell, surrounded by inert carbon, surrounded by a helium burning shell, surrounded by inert helium, surrounded by a hydrogen burning shell, surrounded by a red supergiant envelope that is even bigger than before. And the carbon fusion phase is very inefficient energetically. Much of the energy is carried off by neutrinos. We have huge mass loss and stellar superwinds, and the whole core is converted from carbon to oxygen neon within 1,000 years. And then, well, if the star is sufficiently massive, then we get neon or oxygen fusion. And the process continues. We get neon fusion at 1.5 billion degrees Kelvin, 1.5. If the star is massive enough, the process continues. At 1.5 billion Kelvin, neon fuses to produce oxygen and magnesium. Here, the neutrino flux, remember the neutrinos just penetrate the star and leave, are carrying off a full solar luminosity just in neutrini. You get rid of the neon in just a few years. At a slightly higher temperature, about 2 billion Kelvin, oxygen fusion ignites, producing silicon and sulfur and phosphorus. Here, neutrinos are carrying off 100,000 solar luminosities. You get through with oxygen in a year. The next stage is silicon fusion at 3.5 billion Kelvin. And silicon fusion produces nickel, which decays to iron. And that's an important point. And here, neutrinos are carrying off amazing amounts of energy. And the silicon fusion process is complete in about a day. The result of all of this story is that you have been building up an inert core of iron. The changes are going on very, very rapidly. The exterior atmosphere has far too much inertia to really respond to all these rapid changes. And in the process, the neutron capture slow nucleosynthesis process is producing nucleotides heavier than iron, so this is where a lot of heavier elements get synthesized. And at the end of the silicon day, the day it took to fuse silicon, you have a core, radius of about the Earth, maybe a mass of a few solar masses, which contains the following onion structure. It's got an inert nickel-iron core surrounded by a silicon fusing shell, surrounded by inert silicon, surrounded by an oxygen fusing shell, surrounded by inert oxygen, surrounded by a neon, and so on. You get the idea. And all of this surrounded by a 5 AU or larger hydrogen-helium envelope. The temperatures are now on the order of 5 billion K. Densities in the center are as high as 10 to the 11 kilos per meter cubed. At these high temperatures, the photons that are being emitted are gamma rays, and they cause photodisintegration. So in fact, at this last stage, the star starts very rapidly undoing what it has been doing all these millennia, working to construct heavier and heavier elements. All these nuclei are broken apart. Iron breaks down under bombardment to a collection of alpha particles and junk, and so on. And even alpha particles decompose back into protons. And now, what happens when the combined mass of the star collapses this iron core? Well, you can't ignite new fusion. I mean, you might get iron nuclei to fuse if you try hard enough, but that doesn't produce energy. That won't stabilize the collapse. Once this iron core decides to collapse, it's not really obvious what is going to stop it. We'll see what it is that stops it in the next clip.